Hey guys, hope everyone is enjoying their nice long break and that you're ready to finish up our topic of kinetics and equilibrium. So, we're going to start here. This is where we left off on Tuesday. We talked about equilibrium and what equilibrium actually means. We have that word equal in it, and a lot of us said that it means balance, okay? And that's exactly right. But we have to remember what is equal and what is not equal. So, at equilibrium, we said we have the rates of a forward reaction and a reverse reaction equal. So that means in order for equilibrium to be achieved, we would need a reaction or process that is able to be reversed. So you can look at this as an example. A plus B produces C plus D, but notice that D plus C can produce A plus B. So that would be a reversible process. So we talked about how there can also be physical equilibrium. It doesn't have to be a chemical change like this one. We can have equilibrium between different phases. So at melting between solid and liquid phases, we can have solution equilibrium. So if for every time a particle is dissolving, another one is recrystallizing, then we can have equilibrium achieved then. We're going to focus now on chemical equilibrium, but in any case, we say that if a reversible process has the rate of the forward and the rate of the reverse reaction equal, then you are at equilibrium. So we like to say, or not that we like to, but we get confused because when we talk about concentrations, we may think that they are equal as well, but they're actually not. So you have to remember that if the rate is occurring, the forward is occurring at the same time the reverse is, it means for every reactant you use up and you take away, it's being replenished again at the same time. So you are not changing how much reactant or product you have. If it's constantly being taken away and then replaced, it remains constant. It does not mean that the amount of reactant and product you have is the same as each other. You can have a lot more product than reactant at equilibrium or vice versa. Now, it could be equal, but it does not have to be. So we remember concentrations are constant, and one way we can remember that is the C's. Concentrations constant, rates are equal. And you can see that based on this graph here. We see that the rate of the forward reaction starts off very high because we start off with all reactants, a high concentration. Our reverse reaction actually starts out at 0. There is no reverse because in the beginning we don't start with any product. So as the forward starts going and AB makes CD, AB makes C plus D, A plus B makes C plus D, we're constantly taking away A and B, and therefore less chance of collision means slower rate. So the rate of the forward starts to slow down. At the same exact time, you're building up your product. So now C plus D, you have enough for it to combine and make or react to make A plus B. So the reverse starts to increase until eventually they may reach the same exact rate, and that is equilibrium. So what we're going to talk about now is what would happen if I added a stress onto a system at equilibrium. So what does a stress mean? It's just a disturbance, anything that would disrupt equilibrium, a change that we would add to the system. So that includes things like temperature, change in temperature, change in concentration, or change in pressure. So these are the three things we're going to talk about that can change equilibrium. So think of a stress as a stress how you use it in everyday language. It's something that you would respond to because it's changing or it disrupted your life. Same thing here. The stress is disrupting equilibrium, and so the system is going to change. And what we mean by that is we say that the system shifts to either the right or the left. But what we're really saying is one way, either the forward reaction or the reverse reaction, is going to start happening more quickly, and therefore your rates of forward and reverse are no longer equal. So if we say that a system at equilibrium has a stress placed on it and it shifts to relieve the stress, okay, it's going to reestablish equilibrium, but it's going to take some time. So let's talk about specifically what happens if I change concentration, temperature, and pressure. We're going to start with concentration. So we're going to apply, just like we've been saying, all of this to the collision theory, and it will make a lot more sense if we can envision it. So let's say that I have a reaction and the concentration of either a reactant or product is increased. The reaction shifts away from the substance that I increased. So I want to use this example to show you what I mean. Let's say that I increase the amount of zinc that I have in my reaction vessel. If I increase zinc, that means I have a higher concentration. So I have more collisions happening, which means it's going to shift away from zinc. So if zinc's on the left, it shifts towards the right, which all that means is it's favoring the forward reaction. If I decrease concentration on one side, so let's say I took some solid zinc out, now I have less. Now I have less collisions happening. I have less concentration of zinc. So we say it shifts towards the substance you just decreased. What does that mean? Well, if all of a sudden this has less, it's going to have less collisions, meaning the forward reaction starts to slow down. So the reverse is going ahead. It's staying at the same rate it was, which means it's faster than the forward. So it's favoring the left or reverse reaction. So we say it's shifting towards where I decreased. So we're going to use this to help us. Add, away, take, towards. So let's do some examples. So first example, if the concentration of zinc solid, which is a reactant, is increased, we say add away. So I'm adding on my left side, it shifts away to the right. So it's going to shift to the right side. So this is just if they ask you which way is the reaction going to shift, which way is, which reaction is favored, forward or reversed. So if it's shifting to the right, all that's saying is that the forward is favored. The forward is now going to be occurring faster than the reverse. If I increase the concentration of H2, which is a product, add away. If I add on the right, I shift to the left. So let's think about this. If I increase my concentration of H2, it's going to collide more with my zinc chloride and therefore increase the rate of the reverse reaction. So which way am I favoring? I'm favoring the reverse, which is going towards the left. So you would say that add on the right, it shifts to the left. Now let's talk about decreasing. We said if we decrease or we take away, then it shifts towards that decrease. It's going to replenish it. So if I decrease the amount of hydrochloric acid I have, I take some out, well, now less collisions in the forward, it's going to slow down. So this reaction is going to be happening faster, which means it's favoring the reverse, which is shifting towards the left, okay? So we always say that the forward is to the right and the reverse is to the left. So that's what you have to determine. Which way is going to be happening faster? That's the way it's shifting. So let's say I took away some zinc chloride. Take, towards. So if I take away my zinc chloride, it's going to shift towards it, which means to the right. And again, you always want to think of why, because that's the short answers. That's what we have to be able to explain. Well, it's shifting to the right, meaning the forward is going to start happening at a quicker rate, or it's going to actually stay at the same rate, but because the reverse is slowing down due to less collisions, then the right is going to be more powerful. So that's concentration. We're going to use the same idea to talk about temperature. So if you increase temperature, the endothermic reaction is favored, which makes sense because endo means to absorb energy. So if we have a lot of available energy, so we increase the temperature, then we're going to favor the endothermic reaction. So it's going to shift away from the heat. So again, add away, add temperature, shift away from the heat. If you decrease temperature, you can imagine it's the opposite. So if we have a take away heat, then we're going to favor the exothermic reaction, which is just going to replenish that heat that we just took away, because exo means to release heat to the environment. So it's going to shift that reaction towards the heat. It's much easier to understand when we look at an equation and we see the example. So N2 plus 3H2 produces 2NH3 plus heat. So we see heat here. Now, one thing I do want to review is what kind of reaction is this going forward? Well, if you look, you have reactants, product, heat is a product, meaning that the forward is exothermic, the reverse is going to be endo. I'm adding heat to my reactant and producing my product. That would be endothermic. So let's do add away, take towards. If temperatures increase, we can literally put an arrow right here. Find where heat is. Add on the right side, or my product side, I shift away from that. So I'm going to shift to the left. Think about why. We said if we have added heat, we favor the endothermic reaction, which means my heat is a reactant. That would be the reverse. If I take heat away, take towards, I shift to the heat, which is right, meaning that my forward reaction is going to be faster than my reverse. I'm favoring the exothermic reaction. Last one is pressure. Now remember what we said back with kinetics, that pressure only affects gases. Now the reason for that is because gases are the only type of substance that can be compressed, which you can see in this diagram here. If we take this same amount of particles and compress them, there's enough space to do that. We make the volume smaller and the particles are closer together. So we're actually increasing concentration. So we cannot do this with liquid or solid substances, so keep that in mind. When you increase the pressure on a substance, okay, so this is going to sound a little tricky, but you'll see when we look at the reaction, we say that the reaction shifts towards whichever side produces less moles. And I'll review how we're going to find that. So if you decrease pressure, you shift towards the reaction that produces more moles. Okay, so if you look at your equation and you have the same number of moles on both sides, is it going to favor any which side? No, and therefore the pressure won't affect equilibrium. There would be no shift. So it's like a stress that doesn't affect you. It's going to stay or remain at equilibrium, no shifting. So how do I determine the number of moles? Remember that the coefficients, those whole numbers in front of a substance, represent the mole ratios. So we're going to look at the coefficients on the left side, or the reactant side, and on the right side, the product side, and we're going to compare them. So here's our example. We have the same equation actually that we used for temperature. So first of all, the left side of the equation, you see that there's nothing in front of N2, which we know means 1 mole. 3 moles of hydrogen. So on my total reactant side, I have a total of 1 plus 3 moles, which is a total of 4 moles in my reactant side. In my product side, I have 2 moles of ammonia, and that's my only product. Heat is a product, but it's not a substance, so it doesn't involve moles. So 4 moles to 2 moles. So now let's think about this pressure thing. If I increase the pressure, we said we favor the side with less moles. Let's think about why. If we increase pressure, we decrease the volume. And we know that gases want to spread out. If we have a small volume, I'm going to favor whichever way the reaction makes less particles. So remember we said we can substitute the word moles for molecules here. This way, if I go forward, I'm taking 4 molecules and I'm actually combining them in only 2. So I'm kind of condensing them. They take up less space, because remember, these guys are going to all spread out. 4 things spreading out versus 2 things spreading out take less space. Going reverse, I'm taking 2 and breaking them up into 4 different molecules or moles. So let's think, if I increase pressure, I'm actually decreasing the volume, that inverse relationship. So if I have very small volume, I have less volume, I'm going to favor the least amount of moles, which would be going to the right. I'm going from 4 to 2. So if you increase the pressure, first of all, you have to check, do I have gases? If I don't have any gases, the pressure would have no effect. It would not shift equilibrium. If you had the same number of moles, let's say this was 4 and this was 4, no effect. Equilibrium remains the same. But because we have a different amount of moles, we have to figure out which way would be favored. So we say increased pressure means we want the least amount of moles. So that would be the forward reaction. The forward reaction would shift, or it would take over. It would be occurring more often than the reverse. So equilibrium will be disrupted. If we decrease pressure, now we have more volume. We actually favor the reverse here, or the side with more moles, which would be 2 combining, or 2 actually uncombining to make 4 moles. So we would shift to the left. Last thing we have to talk about is what happens if we add a catalyst. So if we add a catalyst to a reaction at equilibrium, remember what a catalyst does. It decreases the amount of activation energy needed for a reaction to occur, and by doing so, it increases the rate of the reaction. But if you remember drawing these diagrams, it didn't just decrease the activation energy of the forward, it also decreases the activation of the reverse reaction. So because it's reducing them or decreasing them equally, it does not disrupt equilibrium. So if you add a catalyst, let's look at this diagram. I know there's a lot going on. So the effect of a catalyst on equilibrium. So first of all, a catalyst provides an alternative pathway with lower activation energy. That's represented here. So the blue represents without a catalyst, the red represents with one. We see that hump, or that peak, gets lower. I no longer have to gain this much energy. Now I only need this much for the forward to occur. But look what happens also with my reverse. Reactants have to gain this much without a catalyst, or this much with one. So both the forward and the reverse are going to be lowered, the activation energy, which means it's going to increase the rate of both of them by the same extent. So the position of equilibrium remains unchanged, and the catalyst is going to shorten the time it takes to reach equilibrium for both. So if this is without a catalyst and it's showing you the time it takes for equilibrium to be reached, so remember the forward starts off high and decreases as we, take away our reactants, less collisions, it happens slower and slower. While we get more and more product, the reverse can happen quicker and quicker and quicker until they reach the same rate. That's the time when we reach equilibrium. Notice here with the catalyst, the only thing that happened was this yellow line is showing you that equilibrium was achieved faster. But it also just shows you that it winds up being reached at the same exact extent. None of those reactions were favored over another. So the forward and the reverse both increase. Last thing we're going to talk about is enthalpy.